Going over problem 1293, shortest path in a grid with obstacles elimination. I think this is one of the more challenging problems, so this video might be a bit longer as I go through it with more detail. Here's the problem statement. You are given an m by n integer matrix grid where each cell is either 0, empty, or 1, obstacle. You can move up, down, left, or right from and to an empty cell in one step. Return the minimum number of steps to walk from the upper left corner, this corner right here, to the lower right corner, this corner right here. Given that you can eliminate at most k obstacle, if it is not possible to find such a walk, return -1. So here's our first example. Here is the grid. You can see these red things are the obstacles. And the output here is 6. The shortest path without eliminating any obstacle is 10, which would require going all throughout here. However, if you can eliminate one obstacle, which we know based on this k equals 1, then in that case, the shortest path is 6 steps. And that path could be something like, say, going here and then going down here. Here's another example. So in this second example, this is our grid right here, and then the red bricks are obstacles again. And in this case, the output is -1, because given this grid and given a k equals 1, meaning you can remove one obstacle, there's no possible way to get to the end of the grid. So let's take a look at how we might implement this. So here's the initial example we saw. Again, here's the grid, and remember that the grid at first is given as a format of vectors. So here we have a vector containing other vectors inside, and k here is equal to 1. If we aren't able to eliminate any obstacles, we said the number of steps is 10, and this is the way the path would look. Now, if we are able to eliminate an obstacle, in this case we're allowed to eliminate 1, k equals 1, here is our shortest path, or here's one option, and here's another option that's equivalent. Again, both of those take 6 steps. So let's actually look at how we might implement this. Given we're going through a grid and given we're trying to find a path from one point to another, we're going to use a breadth-first search approach. And so for that, we're going to want to maintain some sort of queue where we enqueue a given point to the queue, and then eventually we dequeue that point and try to find neighbors. So let's actually step through this and see how this would work. We're going to start up here at the star at this corner here, so location 0, 0. We'll have a counter for the number of steps. And then here we'll have our queue. So the first thing we're going to do is we're going to enqueue this very first square, this very first position, to our queue. And when we add anything to the queue, the way we're actually going to store it is we're going to store the coordinates, so the row and the column, so in this case 0, 0, as well as the number of obstacle eliminations that we have left. In this case, it starts out as 1 because k starts out as 1 over here. So initially, we're able to eliminate one obstacle because we haven't done anything yet. So we'll add this to our queue. I'm also going to use these markers here to figure out how many steps we're currently at. This will just help us as we work through the queue to increment this counter. So given that there's only one starting point, we'll see that there's only one possible location that would take 0 steps. This starting point here, again, would take 0 steps to get from here to here, and therefore, in terms of our markers, we see that for 0 steps, there's only one possible location or one possible element that actually leads to that. So now, with our breadth-first approach, what we're going to want to do is we're going to want to dequeue that element, and then we're going to want to look for all neighbors for this element. So here is our grid location. And in terms of the possible neighbors, here they are. So here are the 4 possible neighbors for this grid location based on what the problem states. And again, the problem states you can either go up, down, left, or right. So here are the 4 possible locations. Now we have to evaluate which of these are actually valid. So which of these locations can we actually go to? If we take a look here, we'll see that these 2 locations are clearly invalid. If we go through to these locations, we will walk off the grid, so these 2 are clearly invalid. This location is clearly valid, so we can simply just walk over to this location from this point with no problem using 1 step. Finally, we have this downward location. And for this downward location, or this downward direction, it's a yellow arrow because we're not sure whether or not we can actually walk in that direction. And the way we can check is we'll see that we have a barrier here. And so in order for us to actually be able to walk down to this square, we need to make sure we can eliminate the obstacle, or we can eliminate the barrier, which will require us to have some sort of obstacle elimination left for us. And remember that we store the number of obstacles that we can eliminate here. So here we have, you can think of this as a credit or a balance of 1 obstacle that we can still eliminate. So if we look here, we see we have 1, and that means that this location is indeed valid because we have a balance of 1 obstacle elimination, and therefore we could indeed remove this obstacle and walk down. So what we'll want to do now is we'll just want to add those 2 locations to our queue. So first one that we're going to add is 0, 1, 1, which is row 0, column 1, so this location here. And because we didn't have to eliminate any obstacles, we still have 1 in our obstacle balance, meaning we can still in the future eliminate 1 obstacle. And then we'll add 1, 0, 0. So again, 1 is the row, so 1 here, 0 is the column, and here the last element is 0 because we have eliminated an obstacle, and now we have 0 left in terms of our balance of how many obstacles we can eliminate. And now that's it for the number of squares or the different elements we can go to with only 1 step. So we see this was our 1 step section, and now we hit 2 steps. So now when we dequeue our next element, we're going to increment num steps to indicate now we must have taken at least 1 step. And again, we'll just process this element. So here we're looking at 0, 1, 1. So row 0, column 1, and we have 1 obstacle elimination left. So here are the 4 possible directions, and here are the valid ones. So the 2 green arrows are clearly valid. We're able to go left or we're able to go right, no obstacles in our way. Going up is invalid as we'll walk off the grid. And again, with the yellow, we need to evaluate whether or not it's valid. And we'll go here, we see that we do have 1 obstacle left to eliminate, and so this arrow actually is green. We can't go there. So what we'll want to do is we'll just want to enqueue those various squares into our queue. So 0, 2, 1, that's right here. And then 1, 1, 0, that's right here. And then 0, 0, 1, that's right here. Now you might notice that 0, 0, 1 is actually the starting position. That's what we initially started with. We started at this square and we had 1 obstacle we could eliminate. So now we've enqueued a location that's our starting location. And so with breadth first search, one thing we always want to be mindful of is making sure we're not visiting the same square more than once. We're not trying the same path more than once, otherwise we'll end up in an infinite loop. And so here we actually are visiting the same square more than once. So what we want to do is we actually don't want to add this element back into our queue because that's where we started. We already visited that square. And you can clearly see that the square is this light blue color. And so we've already been there. We've already explored the options from this square. So in order to help us, what we're going to do is we're going to use a visited set. And our visited set will take the same form as our queue. So elements in the set will be essentially 3 numbers, row, column, obstacle. And every time we dequeue an element from our queue and visit that element and look at its neighbors, we'll add it to our visited set. So here are the 2 squares that we've already visited. So then we can continue. Now we'll visit 1, 0, 0. And here, one thing to keep in mind is this is going to be our last element that is only 1 step away. And so if we visit 1, 0, 0, that's over here. And then we can actually evaluate the 4 different directions we could go and see which ones are valid. In this case, here are our valid directions. And this time you'll notice that we actually can't go here because we do not have any obstacles left or obstacle eliminations left in our balance. So the only 2 valid directions are going down or going up. So that turns red. And now what we'll want to do is we'll just want to add the 2 valid directions to our queue. So here are the 2 valid ones. So here we have 2, 0, 0, this square right here, and 0, 0, 0, this square right here. So those are the 2 valid neighbors that we can go to. Now, we're done here with visiting anything that is 1 step away. And so that must mean all the neighbors are 2 steps away, and we're done visiting all the neighbors. Now, one thing you might notice is this 0, 0, 0 refers to our starting position. So remember, when we started, the triple we were looking at was 0, 0, 1. And now all of a sudden, we have 0, 0, 0 in our queue. So you might think, well, we're visiting the same place. Again, we probably shouldn't add it. The thing to keep in mind here, though, is these are actually different in terms of the element. So in this case, we actually had 1 obstacle elimination left, versus here we have 0 obstacle eliminations left. Now you can imagine it probably won't be helpful to have 0 obstacle eliminations left. This probably will not be part of our final solution, but if you could imagine the converse, where if you visited something that has, let's say, 0, 0, 2, and now you're looking at something that has 0, 0, 3, you want to make sure you evaluate those separately because one has 2 obstacle eliminations left while the other has 3 obstacle eliminations left. So again, we are looking for unique elements in terms of all 3 numbers, not just the grid location itself. So we can keep going, and using the same process, we're going to dequeue the next element, so 0 to 1. Our number of steps jumps up because we're done processing everything that's 1 step away, and now we're starting to process anything that's 2 steps away. And again, we'll take the same approach, look at all 4 directions, and look at the ones that are valid versus invalid. For any of the valid ones, we'll actually in-queue them to our queue. So here we go. And what we want to do is we want to just make sure before we add it to the queue, let's check the visited set. If we've already visited that location, so in this case 0, 1, 1, we don't want to add it to our queue. So we'll take that one away. However, we will add 1, 2, 1 because we haven't visited that location before. And then we're just going to repeat this process. So here's 1, 1, 0, this square over here, and we'll add it to our visited set. And then we'll just want to see which of these locations is valid. These 3 are clearly valid, and this one, unfortunately, we don't have an obstacle balance left, and so we will not be able to go to the left. So now we're just going to keep going through this process. So here's our next one. So here, this is clearly out of bounds. This will depend on whether or not we have a balance left to eliminate an obstacle, and these two are clearly allowed. And so if we look at that, we can just add the ones that are relevant. And then we'll just keep going with this process. So now we'll go with the 0, 0, 0, so that's over here. Make sure to add it to our visited set. And we look at all possible options. Again, given we have no obstacle elimination left, we won't be able to go down. And given that this location has already been visited, we won't be able to go there either. So now we move on to 3 steps. And again, we just increment to now indicate that we are 3 steps away. So it'll take 3 steps to explore any of these squares. And then we just keep processing. So we'll DQ, add it to our visited set, find the square, and look at all possible directions, evaluating whether they're out of bounds, possibly allowed, visited, or entirely allowed. We'll keep only the squares that are allowed, and we'll add them to our queue. Then we'll keep going. So we'll DQ the next, explore all possible squares, add it to our queue, add whatever is allowed to our queue, and then keep going. So here's our next element, 1, 2, 0. So that's going to be right here. And here are the possible squares. Here are the ones that are valid. Let's add those to our queue and then keep going. So we DQ, we look at this location, 2, 1, 0. Here are possible squares. Here's the valid one. And we will just repeat this process. So I'm going to go through this a little bit faster. So 3, 0, 0. There are the possibilities. There's the one that's allowed. And now we'll see, looks like 2, 1, 0 is our next element, but it's already been visited, so we don't even need to process it. So we keep going. Now we're at 4 steps. And here is 2, 2, 1. So this is right here. We will explore all possible directions. And looks like 2 are valid, so we'll add those to our queue. And then here is 0, 2, 0. 2, 2, 0. So 2, 2, 0 will be right here. Add it to our visited set. Explore all possible directions. None are valid, so we just keep going. Here is 0, 2, 0. So that will be right here. We see that this has actually already been visited, so we don't even need to do anything. And we'll keep going. So here is 2, 2, 0, so that'll be right here. And we check, has this already been visited? It looks like it already has been visited, so we won't even process it. Here is 4, 0, 0, it hasn't been visited, so we add it to our set, and we look to see what are the possible directions. And we'll keep going. Now we're at 5 steps. So let's DQ the next one. So 2, 1, 1, we'll add it to our visited set. Explore all possibilities. Looks like there are 2 directions that are valid, so we'll add those to our queue. And we'll keep going, 3, 2, 0. That to our queue. 4, 1, 0. Add that to our queue. And now we're at 6 steps, so we keep going. 2, 0, 1, so that's going to be right here. Looks like none of these directions are valid. And 3, 1, 0, again, none of the directions are valid. And 4, 2, 0, we look at that, and actually that is our final destination, so we've made it. So now we'll see we've reached our goal where we wanted to get, and now we can see it took us 6 steps to get here. So let's take a look at how you might code this up. Again, this is a slightly harder problem, so go a little bit slower on this section. So what we want to do is we want to implement the same logic from that walkthrough into code. So let's start by declaring some variables that might be helpful. So first of all, let's get the number of rows based on the grid. So this is the number of rows, and then we'll also get the number of columns. So here are rows and columns. The next thing we want to do is remember that at any position we can walk up, down, left, or right. And so the way to do this is we just want to list these 4 directions in some way that we can use the grid to explore those 4 different directions. And so the easiest way to do this is actually just having a vector of pairs, and each pair will have 2 ints. Call this directions. And first we will have 0, 1, then we'll have 1, 0, then we'll have 0, -1, and then finally -1, 0. So this will allow us to explore all 4 directions, and the idea is either we're moving, say in this case, either we're moving up a column or down a column, or we're moving to the right or to the left. So let's keep going here. The next thing we're going to need is we're going to need to keep track of anything that's visited. So in this case, I will use a set. So here's a set, and we're going to store this set as containing vectors of ints. And this will be useful because remember that we want to have each element as a triple. And so what it's going to have is each element is row, column, and then obstacle. And so this will allow us, with a vector, we can store all 3 of these together. So now that we've have that, the last thing we're going to need is we're going to need the number of steps. So that's going to be a counter that starts at 0. And finally, our queue. And so our queue is going to be the same thing, where it's going to store vectors of ints, and I'll just call it queue. So to start out, we want to initialize the queue as containing just one element, which is this element here. The way we'll do that is we're going to use queue.push, and then when we push the element, in terms of its coordinates, so its row and its column, that will be 0, 0. In terms of the number of obstacle eliminations it has left, that's just going to be k. So we're going to add k here. So this is how our queue starts. Now what we want to do is we want to actually start processing the queue. And remember that each iteration is going to process a single step. So processes all, let's say, elements within num steps from origin. This will make a little bit more sense in a second. So what we want to do is, while the queue is not empty, what we need to do is we need to process all of the locations that are exactly num steps from origin. And so we can take a snapshot of the queue by taking the size of the queue. So something like this. And once we have the size of the queue, we can actually go through every element for that size. And the last thing is, now that we have that, at the end of this iteration, that's when we actually can increment num steps. So we'll do num steps plus plus. And in here, this is where we actually are going to process each element and explore its neighbors. So first thing we need to do is we need to pop off the current element. So we'll call it cur, and we'll use queue.front to actually get a reference to it, and then we can use queue.pop to remove it. So now we have a reference. Next thing we want to do is we want to check, have we reached our final destination? So check if reached the end. And what we'll do here is we can just check that the coordinates are equal to the coordinates of this final destination. So in this case, that's going to be cur 0 is equal to rows minus 1. And to be certain, let's just put parentheses. And in addition, cur at 1 is going to be equal to columns minus 1. So this is how we know that we've actually reached the very end. If that's the case, we just want to return num steps. Now, if we haven't reached the end, we want to explore all possible directions. And this is where our vector here with the directions is going to come useful or come in handy. So here I'm going to say explore all possible directions. So here we can go for every possible direction. So inside of our directions vector, take out the space. What we'll want to do is we want to have a new x, which is going to be the current x, or so we can even call it new column. That might be better. New column, current, which is the current column, plus whatever direction we're going. So that's direction dot first, and then new row, and this one's row, and this one's column. Then this is going to be 1 plus direction dot second. So this is our new row and our new column. And then in terms of the number of obstacles, so the balance we have left, that's always just going to be cur at index 2. So now that we have that, what we need to check is we need to check whether this new location, so the new row and the new column location, is in bounds. And so the way to do that is we'll want to check is new row greater than or equal to 0, and is new row less than rows, so the number of rows, and is new column greater than or equal to 0, and is new column less than the number of columns. If that's the case, that means this is in bounds, so it's not going to have a red arrow as we saw in our diagram. The next thing we need to see is, do we need to have an obstacle balance in order to be able to go through it? So the way to do this is we're going to use our grid up here, and we're going to check, does the location we're trying to go to, so our new row and our new column, is it empty or not? So is there an obstacle there or not? So the way to do this is we can use new row and new column and check if that's equal to 0. So if this is the case, that means this square is empty. There's no obstacle. We don't need to worry about going through. And so now the next thing we want to check is we also just want to check, have we visited this location or not? And the way to check that is we can use, I'll use the count method. And then what we want to check is new row, new column, and then obstacles. I'll move this over a little bit. So if this is the case, that means this location has no obstacle, so we can easily pass through, and we've never been there before. So we'll just add this as a new possible neighbor to explore. So this is going to be new row, new column, and then obstacles. And then we just want to mark this as visited. So visited.insert, and we will insert the exact same thing. Now the next case is whether or not the location actually does have an obstacle. Can we still get through? So in this case, what we want to check is this here, is this new location, if it's equal to 1, and we actually have an obstacles balance left, so obstacles is greater than 0, meaning we do have some balance left. And then lastly, that we haven't visited the location before. So that's the last condition. And this is going to, in this case, be obstacles minus 1. And if that's the case, what we'll want to do is we'll want to add this to our queue. So it's going to be new row, new column, and then obstacles -1 to indicate that we just went through an obstacle and we used one of our quota. And then finally, we're just going to insert this into our visited list. So this is new row, new column, and then obstacles -1. So now in this case, we've marked it as visited. The last thing we need to do is what happens if we can't actually traverse through. In that case, what we want to make sure is we return -1. So if we don't ever return in this check over here, that must mean that there's no possible way for us to actually get through. And in that case, we should just return -1 at the end. So this is our final solution. Let's submit it and test it out. Looks like I am missing a parentheses. So here, either an extra one. Looks like I'm actually missing this here. So let's try again. Awesome. So here's our final solution. Thanks for watching, and feel free to comment if you have questions.